Welcome to this seventh in our series of lectures on risk. Last week we dealt with the malicious creation of risk through terrorism. This week, even if we aren't going to use the phrase acts of God, we're going to deal with risks of natural catastrophes, and with the Haitian earthquake and the mudslides in Madeira fresh in our mind, it is very pertinent. But in particular, we're going to deal with that most extreme risk, which has altered life on the planet pretty fundamentally, at least once, which is the risk of being hit by something from space. And our speaker tonight is Professor Mark Bailey, who's the director of the Armagh Observatory and a well-known publicizer of science. He did his first degree at Cambridge, did his doctorate at Edinburgh, came back to Cambridge, and then eventually has ended up at Armagh. His early work was on very distant galaxies, but it's been moving steadily closer to the solar system and to the origins of comets and of asteroids. And it's been moving even closer, of course, to the possibility that one of them may thump into us again. And I think this is the point at which I look you all in the eye and say that the emergency exits are there. And introduce Mark Bailey. Thank you very much.
Thank you very much. Thank you. Well, thank you very much for that introduction, and thank you too for the invitation to present a talk at this series. It's a great privilege to be able to do so. What I'd like to do in this talk, I'll just go back to the view again, is to introduce the canonical framework for describing risk in the context of major societal events. And then I'd like to broaden the discussion to include the implications of natural disasters ultimately triggered by events occurring outside the Earth in our solar system. Things coming from outer space trump, in terms of magnitude, the worst possible hurricanes and earthquakes, and have the potential, as was mentioned a moment ago, to cause mass extinctions of species, and in fact to change the course of evolution of life on our planet. And a very appropriate topic, it seems, for a Darwin lecture. In the last part of the talk, I would then like to conclude on a more speculative note, highlighting the fact that there are more uncertainties, even in astronomy, than most experts are usually prepared to acknowledge, and that raises the uncomfortable question of limits to knowledge and how best we can plan for the unknown. So the long view of astronomy, or represented by astronomy, raises many questions for risk assessment, for how we perceive ourselves, and for our long-term views on the development of society. For example, do we ignore rare high-consequence hazards that have an extremely low probability of occurring in your lifetime or mine, or even those of our children or grandchildren, palming the responsibility, as it were, for managing the risk onto successive generations? It also raises the question of how much we should do to help quantify potentially global hazards when we have relatively few resources at our disposal, and when our country is, in any case, only a very small fraction of the whole world. So, for example, who should take care of global hazards? Are they our responsibility or those of others, perhaps those who are more likely to be affected by such hazards? And having identified a risk, as it were, by blue skies research, or more accurately in astronomy, by dark skies research, how rationally do we quantify the additional resource that should be directed towards the problem in order to achieve the objective of first fully understanding the potential risk and then putting in place appropriate countermeasures to mitigate that threat, leaving aside the question whether those measures might themselves have consequences which are risky in themselves. Finally, in dealing with the long view, it seems to me that we should possibly consider human life and civilization as if it were an organism with a potential lifetime measured in thousands, if not tens of thousands of years. And I would raise the question, would such a creature with a memory, as it were, of natural catastrophes extend in thousands or even millions of years, and a future life just as long, respond differently to long-term risks than we do, whether as individuals, national governments, or United Nations? So this slide, let me begin by unpacking the title of the talk and considering what I mean, or what we mean, by natural catastrophes. I suppose everybody knows what is meant by the phrase. It's an event outside our control that totally changes the circumstances or the environment in which we live. Natural catastrophe is often accompanied by significant loss of life, but with appropriate warning and or countermeasures in place, this can usually be mitigated. And appropriate warning, oops, sorry about that, come back. That's the one. With appropriate warning, this usually means that we have at our disposal anyway, some form of scientific understanding and of the factors that led to the event occurring. Another aspect of these natural catastrophes is that they're short-lived. They occur on timescales sometimes of minutes, hours, or at most days, and are essentially totally beyond our control and beyond any conceivable technical fix. The only solution, really, is to live in places where such events don't occur. And yet, we don't do that normally. I mean, here's the example of the San Francisco earthquake. You have spectacular scenery. A lot of people like to live near volcanoes in the countryside, as it were. You have floods, which you can't avoid, and in this case, tsunami. So although the logic would tell you to avoid such places where such risks may occur, we nevertheless have built in to the human psyche, as it were, the acceptance of such risks and an almost fatalistic willingness to take the hit when it occurs on the basis that, well, we had a good life anyway, and maybe actually the big one won't happen during our watch. Another point, which I underline in this picture, is that such risks are common. And that allows us to do statistics on them. And despite the idea that these risks they're common, they're often reported, in fact, they're very localized. And thankfully, if we could use the phrase that the government has sometimes used in this context, thankfully, they don't occur near us, at least most of the time. And so that's the general picture of natural catastrophes. They're sudden, there's no warning, they're high impact, but on the positive side, they're local, they're relatively short-lived compared with the intervals between them, and they're amenable to scientific study and direct observation. And really, we have this opportunity to study the risks and really to get warnings of them and hopefully remove populations away from them. There's another class, if you like, of natural catastrophes, which I've described here as unnatural natural catastrophes. And here, the aspect of suddenness is not the case. It's often a slowly acting process, and there's plenty of warning. For example, we have climate change. We're all affected. The climate change affects the whole globe. It's not a local phenomenon at all. And we have no recent experience of such events, particularly of their seriously adverse effects. And so, again, we have an inevitably, it seems to me, more subjective reaction to the risk. Maybe that it won't happen, a denial reaction, or again, fatalism. Again, there's nothing we can do about it. And again, we rely on science to try to understand these sorts of risks, but there's much greater scientific uncertainty attached to them because we simply don't have recent experience of them. We don't really constrain our scientific theories by observations. We're forced by circumstance to extrapolate our science in order to explain or possibly understand the consequences of these slowly acting natural catastrophes. And here, maybe history is our best guide, because thinking again of civilization, as it were, as an organism with a lifetime measured in millions of years, if we have historical sources which tell us about such things that did happen in the past, maybe we can interpret them in terms of our modern understanding. Well, turning back to the first part of the talk, the name of the talk, what is risk? There are really, when somebody like me talks about risk, or maybe someone like you, we don't always necessarily know what we're talking about, if you'll excuse me applying that to yourselves. What is risk? It is a word which has many different meanings in common parlance, and you only really have to look at the two dictionary definitions above to see what I mean. The Chambers gets it more or less right, whereas the Oxford Dictionary is merely the possibility that something unpleasant will happen. In a way, you've all taken a risk in coming here this afternoon in the hope of getting an entertaining talk. Here we are. Maybe it won't be quite what you were hoping for. The Treasury has a keen interest in risk, and it defines it in the following way: uncertainty in outcome, whether positive opportunity or negative threat of actions and events. And it seems to me that one way, perhaps the closest analogy and best analogy, is an insurance analogy. Here, in order to insure our houses or whatever, the insurance company defines the risk, defines the circumstance, in fact, of what might happen in the small print. It has an idea from statistics of the probability of such phenomena occurring, and that allows it to estimate the risk and therefore attach a premium to the risk. This is a way, a monetary attribution to risk, which allows different risks to be ranked and allows us to decide, in fact, whether some events, some risks are down in the noise or whether they're significant enough for us to worry about, and therefore, in some sense, to see the wood for the trees. There are many examples of actions or events of which the consequences or maybe the probabilities are very subjective. And I mentioned already that the government is keen on risk. The Health and Safety Executive is keen on risk, and going back many years now. And as I say, in specifying the risk, there are two major components to the issue of risk. If we just say it's the chance that something will happen, that's actually not good enough. What we need to do is, like an insurance company, we need to specify the circumstance and the probability. And therefore, there are two separate components, distinct components, in everybody's concept of risk. And in this case, the tolerability of risk. Risk is the probability that a specified undesirable event will occur in a specified period or as the result of a specified situation. And in order to apply that in practical terms, quite often you introduce the idea of a risk matrix. Therefore, where one action is the impact, one axis, the other is the frequency or probability of the event. And I mention this one because this is the risk matrix that the Armagh Observatory is obliged to use by government. We don't have any choice in the matter, but you might note that the high impact, here we are, high impact, risk factor 5, resulting in failure of key observatory or departmental objectives or financial loss exceeding several millions, if only that were possible, or public embarrassment or media coverage, where sometimes we seek that, or attention from the Assembly or Public Accounts Committee, or even death. And then you have the frequency. Low medium means it might conceivably occur at some time. And well, actually, that means it probably will occur once or twice. And in that sense, this sort of risk is a very high one. And when you're thinking of natural catastrophes, which by their nature are bound to involve multiple deaths and might conceivably occur at some time, one's almost forced to adopt a red risk and therefore consider the mitigation measures that you might want to implement. And the government therefore encourages us to plan for the possible impact of events like swine flu, storm, flood, and maybe other sort of catastrophes which aren't necessarily of a natural kind. But the larger natural catastrophes don't figure on our risk register because they're not our responsibility. The sorts of risks that are taken by government as a responsibility rather than by individual organizations are referred to as societal risks. These are risks whose consequences of the event affect many people simultaneously. And developing the idea that most natural catastrophes are localized, occur unpredictably and without warning, and that the risk has these two components, the impact of the event and the probability of it occurring, you normally find these societal risks plotted not so much as a matrix, but on a graph. And in this case, coming from the UK National Risk Register, you'll see the relative impact without a scale, and a relative likelihood with another lack of scale, but you get the idea that electronic attacks, attacks on crowded places, pandemic flu are quite likely, whereas major industrial accidents are less likely but maybe quite high impact. Quite why major transport accidents are over there, I'm not sure. But you nevertheless get an idea of ranking risks according to some objective criteria of frequency and impact. The Health and Safety Executive, again in the Tolerability of Risk document, and this was brought to my attention really by Nigel Holloway in 1997, where he introduced this in the context of astronomical risks. In a way, it's a very, very good way of looking at the insurance. It's another way of looking at the risk from an insurance perspective, the actuarial approach. If we could agree, for example, on the value of a human life, then together with the frequency of risks, or I use the word loosely, the frequency of events which lead to large numbers of fatalities, that would allow us to estimate how much money we would normally be prepared to pay to avoid such risks materializing. So, for example, go back. If you consider this one here, 100 deaths every 1,000 years, and if you regard that as at the boundary of intolerability, then strange noise coming from my side here. If you consider this to be the boundary of intolerability, so you could barely live with that, 100 lives being lost every 1,000 years, then you would be, and if the value of a human life, for example, were 1.5 million, then you would be prepared to put in countermeasures costing of the order of 150,000 a year in order to avoid that particular risk. Now, it raises many questions. What is the value of a human life? If it's my life, it would be much more than 1.5 million, and possibly you'd think the same. And then it raises many ethical issues. For example, is there even the idea of a constant value for a human life? Obviously, it could be an average. Does it depend on the lives in question? Does it depend on their income, their employment, their place of birth, their contribution to society in some general sense? How do you apply this actuarial approach to situations of high risk, high numbers of possible fatalities? Leaving that aside, this whole idea of a frequency an N diagram, number of deaths versus the frequency of occurrence, is actually a very valuable way of ranking different kinds of natural catastrophe. And risks can be deemed intolerable if the frequency of N deaths is too high. They can be deemed tolerable In other words, below the negligible line if they're down in the noise. And in between, you would seek to reduce the risk to some acceptable level, as low as reasonably practicable. And that's really what we do in our daily lives, insofar as all risks, and the government is doing something similar in this context. So, with that introduction to risk, let me now move on to the apparently more secure ground of astronomy. And in this case, I think it's fairly clear that astronomy trumps any Earth-based cataclysm that you might care to name. And one way of illustrating this is simply by this idea of the death of the dinosaurs, which took place around about 65 million years ago, the impact of a comet or an asteroid on the Earth. And what did it do? It wiped out large numbers of species at a stroke. Not quite overnight, but at a stroke. And this changed the course of evolution of life on Earth and led to the opportunity, if you like, of humans like ourselves appearing on the scene. Thank you. Yes. The Earth is a bombarded planet. I'm not saying these are dinosaurs. These are pterodons, I think. But nevertheless, if you just look at this picture, here's the canonical 10-kilometer diameter asteroid. There's the mile-high tsunami beginning. And these things will probably have already been extinguished by the heat generated by this object coming in through the Earth's atmosphere. There's another asteroid coming in here, which is rather strange, considering that it should be a random asteroid. But maybe that's already giving you some insight into the way astronomers are thinking, and that maybe it wasn't a single unique object coming in. Maybe it was a cluster of objects. Nevertheless, the Earth is a bombarded planet. The evidence for the bombardment is there not quite for the eye to see, but for scientists to discover. And some areas of the globe, some parts of Africa, Australia, the North America and places, are very, very old, and they therefore still have the record of the impacts that have occurred over geologic time. There are around about 175 known large impact craters on the Earth now. If you look at the Moon, what you see is the residue largely of the bombardment phase when the Earth and the Moon were still quite young. And for every crater you see on the Moon, just on size grounds alone, you would expect the Earth to have been struck approximately 20 times as often. And in the distant past, when the Earth was being bombarded at that rate, the Earth, even if it was hospitable to life in the first instance, was sterilized by the very large flux of impacts that was taking place at that time. And subsequently, life on Earth got going, as many of you might know, very soon after the Earth became potentially capable of sustaining life. And from time to time, subsequently, there have been occasional large impacts, like that one, which is the one responsible for the extinction of the dinosaurs, according to the current theories. There's another big one, and a few other large ones. But so some of these large-scale impacts have the possibility not just to cause fatalities amongst humans, but actually to extinguish whole species. And in that sense, such impacts would be intolerable in every sense of the word, and it really means, however low the frequency of the impact, the level of the risk, the consequence, is so vast, infinite, that the risk is finite, and we should really try to do something about it, if you think prolonging the species is a sensible objective in the long run, which you might not. Okay, so what are these objects that are potentially causing the astronomical risk of natural catastrophes? We call them near-Earth objects. And basically, they are any astronomically small body capable of passing close to Earth. They include comets, asteroids, and fragments of comets or asteroids, and even asteroid-like, dead or inert devolatilized comets. And then there's another component, which I've not mentioned here, which is the dust. The dust liberated by comets, which can float on into the Earth, be accreted by the Earth, and produce a kind of stratospheric haze layer if the dust was a significant enough flux. The near-Earth objects range in size from houses to mountains, from sizes of tens of meters up to kilometers or more. Where do they come from? The asteroids, by and large, the asteroids come from the main asteroid belt between Mars and Jupiter in the solar system. The process is rather complicated, but usually boils down to a collision between such asteroids in the main belt, a random effect, totally random, unpredictable really, and then the disturbance of the fragments in the resulting fragments in their orbits leads them to evolve onto unstable orbits, ultimately to become planet-crossing and potentially Earth-crossing. The comets have a variety of sources. The main one is the Oort cloud, a vast swarm of such cometary bodies extending halfway to the nearest star, part of the solar system, and a secondary component is the Edgeworth-Kuiper belt, which is the region rather beyond Neptune. What do they look like? Well, here are some spacecraft images by various spacecraft have been to comets or flown by them, or been to asteroids and flown past them. Here's a lovely image of Halley's Comet in 1986, and then you see one or two others. The scale of this is 16 kilometers long. In these cases, these are of the order of 5 kilometers across. So you get some idea of the diversity of the cometary objects. The asteroids, here's Eros, and here's Ida with its satellite Dactyl. This one's around about 30 kilometers, and this is about 60 or so, if I remember correctly. So they're very diverse, and even the asteroids and the comets are cratered by smaller bodies running into them from time to time. How many objects are there? Well, the main belt asteroids were the first one was Ceres, was discovered in 1801. Most of the objects were found occupying very, very stable orbits between Mars and Jupiter. Their orbits are as stable, if you like, as those of the planets. It wasn't until 1898 that the first object outside of that zone was discovered, namely Eros, that's the one you saw a moment ago, and then another 34 years went by before the first Earth-crossing asteroid was discovered. And by 1970, around about 30 had been known, or were known. And on the basis of that 30, astronomers made the estimate of how many there were in total in the population. And the answer was there were to be around about 100. But by 1990, that number had been surpassed. And so that also indicates, to some level, the caution that should be attached to people who make grand statements, extrapolating on the basis of relatively limited knowledge. By this time, there were surveys being put in place in order to discover asteroids, and the discovery rate went on much faster in a growing fashion, so that by today, there are nearly 6,700 or more objects known, out of a total asteroid population of the order of 500,000. So it's really needle in a haystack stuff discovering these objects. And on the basis of these 900 or now 6,500 or more near-Earth objects, the number larger than a kilometer is thought to be of the order of 1,000. There's some uncertainty in that number, depending on who you speak to, but that's the order of magnitude of the number. And the mean collision frequency with the Earth is once per 200,000 years. Now, this little movie, if I can make it work, which I do, this will show you the rate of discovery of asteroids. What you're seeing here is the Sun, Mercury, Venus, Earth, and Mars, and Jupiter. And now you see the first 4 asteroids discovered around the turn of the 19th century, Ceres, Pallas, Juno, and Vesta. And gradually all these green ones are the main belt being discovered throughout the 19th century. And what you can note, really, is here in this movie, is how many main belt asteroids are being found and how few are the objects outside of that zone of the solar system, that stable zone. There are increasing numbers, nevertheless, of objects forming, or not forming, I mean being passed onto orbits that become Earth-crossing. And as the camera, as it were, pans away from the thing that zooms in, you can begin to see how many objects there are now on Mars and Earth-crossing orbits. And these objects have quite short dynamical lifetimes compared to the age of the solar system, measured in millions of years rather than the billions of years for the lifetimes of the main belt objects. Okay, so there's very large numbers of objects now known, a growing number. What would be their effects were one to impact on the Earth? The diameters of the objects are estimated to be in the range, small ones, 50 to 100 meters, houses, or maybe a big house, up to mountain size down here. If you're at the small end of the range, the energies are of the order of 10 to 100 megatons, and they will make craters, if they reach the ground, which not all of them will, up to 1 kilometer across. The rule of thumb is the crater is roughly 10 times the diameter of the object. Other things being equal, the comets are more dangerous than asteroids because they come in faster than the asteroids. But on the other hand, maybe they're not so dense. So again, it depends on the circumstance of the individual object. If the diameters are larger than that, then you'll get much larger craters, up to a few kilometers, and then you start to destroy areas as large as a large city or a small state, like Northern Ireland. Oceanic impacts produce huge tsunami, and as you get up the scale in size, the energies become almost unimaginable in size, and the craters, which you see plenty of on the Earth, up to 20 kilometers, and the tsunami then reach ocean scales. And above this size, a diameter of the order of 0.5 to 2 kilometers, a critical size, really, above that size, the impact, wherever it happens on the Earth, will have an effect wherever you are. It's a global reach phenomenon, whereas the smaller ones are much more in the category of ordinary, run-of-the-mill, as it were, natural disasters. Above about 1 kilometer, with some uncertainty, you reach global scales. And then you get up to the largest objects, 5 to 10 kilometer size objects. They have the capacity, anyway, to produce mass extinctions. Fortunately, the largest objects are the rarest and the most infrequent, and it's fortunate that they're the largest objects. They're the easiest things to discover in space. And so, in a way, we are fortunate living on Earth faced with this kind of risk. We have the possibility to discover all the large objects in space of a potential to cause such a massive impact, and then ask the question, is any one of them now on an orbit that could intersect the Earth at some foreseeable time in the future? And expecting, if you like, that the average interval between such major disasters is measured in tens or maybe hundreds of millions of years, we would be pretty unlucky to be living at a time when one of those things was due. So we've got a lot of things, positive things, if you like, going for us. But nevertheless, impacts do occur. And this slide and the next one just shows a couple of those. This is one example of an impact. We haven't had a kilometer-sized object running into the Earth in the scientific period, but the Jovians have. And in this case, the Jovians had a bad luck experience. There was discovered in 1993, this comet, and it was a funny one. It had this funny appearance with multiple fragments inside its trail. And it turned out they were all on orbits that were inevitably destined to collide with Jupiter. Had you asked an astronomer in 1992, what was the chance that 21 objects of a kilometre or half a kilometre in size would run into Earth in the space of a week in the foreseeable future? Well, they would say, well, on average, you'd expect one event every 2,000 years or so, and therefore, the 21 would be very minute in the course of a week. But actually, in this case, it happened. And the reason it happened was, one, the orbit, which was destined, in a sense, to collide with Jupiter, and the other, the breakup event. The object had gone round Jupiter in 1992. It was so close to Jupiter, and the comet was so fragile that it split the fragments up, split the nucleus up into many fragments, and thence the fragments were destined to run into Jupiter. This shows you a couple, actually, of 20th century impacts. The Tunguska one, 1908 in June, flattened an area roughly equal to the area enclosed within the M25. It destroyed the forest. It had a blast equivalent of around about 5 or possibly 10 megatons. And had it landed over London, which of course was unlikely, it would have destroyed that whole area. And so this shows, if you like, the risk of small objects hitting the Earth. Most likely they're in remote parts of the Earth where they cause not much harm. And here's another one in 1947, a painting from the Russian Academy of Sciences, just showing the appearance of such an object, a small object in space which makes its way all the way down to Earth. So what's the actuarial cost in this case? Well, we should expect the premium to cover the losses. The collision rate is 1 per 200,000 years, and if you assume for the UK that a quarter of the people would be killed by a kilometre-sized object, either due to the impact alone or due to the climate change resulting from the impact, then and as I mentioned, the actuarial cost of a life, then the average cost of the insurance is £100 million a year. And that is therefore the order of magnitude of the money that society as a whole should be prepared to insure itself against the risk if such insurance is possible. And it raises, excuse me, I'll go back one more. It raises a number of important questions. This is a world risk, so the real cost is much higher for the whole world. But on the other hand, is it our job to protect the world? Probably not. Maybe if you have the responsibility, it is. And also, as impacts occur so infrequently, once every couple of 100,000 years or more, we can safely ignore them, surely, trusting to fate. And so it raises all sorts of questions as to your response to the probability of the occurrence of a particular event and mine. You know, do we take the long view? Do we try to secure civilization on the long time scale? Or do we simply say to ourselves, well, it's probably not going to happen to me, so I'll just carry on in the hope that it won't happen to me? Rather like you or I deciding not to take out house insurance for fire or something. It's probably not going to happen. But on the other hand, if it does happen, then it's a risk that you can't afford to not have covered. And then it raises questions, well, what can you do about the risk? Which maybe I'll come back to later. You might also argue that the risk itself is actually unbounded because of this question that when the impacts occur on the Earth, there is a potential for the extinction of the species. And in that sense, it's unbounded. But again, it raises this question as to what value you or I put on the human species extending indefinitely into the future. Most species on Earth, after all, have become extinct, and that's the likely outcome for the human species unless they intervene in the normal process of natural evolution. So looking at the FN diagram again, where do the asteroids sit? Nigel made a nice statement. I'm not sure if I've quoted him perfectly accurately, but the point was, if you had a jolly wheeze, if you like, of making money, and you could launch 1,000-kilometre-sized asteroids into space onto Earth-crossing trajectories, actually, you wouldn't be allowed to do it. It would be seen to be too risky a venture, not for you necessarily, financially, but because the risk falls hugely in this intolerable zone. In other words, 10 million deaths every 100,000 years or so is simply not acceptable for a business, even if it's only every few 100,000 years. And again, you're dealing with very, very low probability events. But this is the level of probability for which we routinely try to design, for example, nuclear reactors, make sure they don't die or explode on timescales more often, on average, than once every million years. Okay, so I would like now, in the final part of this talk, to try to, rather than dwell, as it were, on the impact of asteroids and comets on Earth, there are many people better qualified than me to talk about the environmental aspects of that. But what I'd like to do now is just talk about how this whole picture that I've described, which is a standard view, really, how it fits into a broader astronomical picture. And I suppose I would like to start by just pointing out that astronomy now is in a golden age, where the separate strands of interest that motivate one's wider interest in the subject, the cosmological strand, quasi-religious, if you like, the question of origins, all of that hangs together as one important strand of interest, which goes back thousands of years into our cultural heritage. The second major strand, the astrophysics strand, the study of everything in the universe, that also is on an exponentiating trajectory of interest. Almost every few months or years, there's some new discovery which makes the news about objects in space and their interactions one with another. And then there's the third strand, the spin-off strand, which is how do you get benefit from astronomy? And that spin-off is huge, not just, for example, in understanding how spacecraft operate and are orbiting around the Earth and the benefits of Earth observation, but also insofar as that astronomy plays a major role as an imagination driver in science. It's a laboratory where you can test your theories to destruction. And also in the humanities, it's an imagination driver, for example, for the work of artists or poets, musicians, and philosophers. And then the spin-off into education and the idea that astronomy is one of those things still that people like to attract or find is attractive to young people, diverting them into the scientifically interesting subjects which actually have economic benefit for the country as it needs to be in a competitive world that we live in. And in such a subject, such as astronomy, going through this golden age, it is almost bound to be the case that there are uncertainties. In fact, it's the job of an astronomer to overturn old theories, replace them with new ones. That's the way we make our business. New theories for old. And so whenever an astronomer or even a scientist of any discipline presents an extrapolation from theory, you should immediately be dipping your finger in the pot of salt and asking the question, well, yes, it is an extrapolation, and also how reliable will be your assumptions in 10, 20, 30 years' time? And if we're assessing the impact hazard, which naturally is talking about timescales of hundreds or thousands of years or more, then really we need to take a much longer and more sanguine view, if you like, about currently accepted theories. It's almost like the point made by Donald Rumsfeld, and I'm not sure if it was mentioned in one of your earlier lectures, about the known knowns and the known unknowns, and what about the unknowns that we don't know about yet? How really do we fold those sorts of uncertainties into the story of the risk and the actuarial risk, and the accounting, if you like, the ranking of the risks that are important and the ones that are less important to look at. And so in the last 10 minutes or so of the talk, I want to, first of all, just point out that the NEO hazard is unique, and then talk about some of these uncertainties, if you like, in the astronomy, focusing on the area of my interest, namely comets, and presenting a broader historical perspective for that. The hazard is unique because it's potentially unbounded, and therefore not just civilization but survival of the species is at stake. The impacts are predictable, and they're predictable years in advance given sufficient knowledge of the NEO orbits. And they're avoidable given enough warning. In other words, you can mitigate the risk, most of it. For example, a simpler way, you could move the population from ground zero. You could store food supplies. And you can deflect NEOs in space. And that raises a whole bunch of very interesting questions known as the deflection dilemma. Because if you can deflect things away, then you can deflect things towards. And there are many more objects, small ones especially, which you would like to deflect, possibly, you would like to deflect onto Earth and explain as a natural catastrophe, perhaps. So there are all sorts of interesting questions that this sort of subject can raise, and it requires, therefore, firm international control. Now to come to the astronomy. Let me just talk about the comets. The size distribution is very large. There are now known to be giant comets with sizes bigger than 100 kilometers in all the cometary sources that we know about. And therefore, we compare that with the smaller asteroids that we know about in the near-Earth object space. The cometary evolution is highly chaotic and therefore unpredictable in the long term, and as evidenced by the Shoemaker-Levy 9 event and other streams of objects, such as the comets that are falling into the sun on an almost daily basis, known as the sun grazers, comets are very fragile, easily broken up in space, and they have short lifetimes, a few thousand years at most. And that's a timescale of interest for civilization. And therefore, the comets that we see now are different from the comets our ancestors would have seen 4,000 or 5,000 years ago. And the last point about comets is that their evolution and decay leads to streams or trails of debris, and therefore non-random impacts on Earth, such as the meteor showers you're familiar with, the annual showers, and also the SL9 event on Jupiter. One such example that illustrates this is an object called Chiron. It's actually known as a centaur. It has a present orbit somewhere with the closest approach to the Sun near Saturn and an aphelion furthest point much farther away. And if you integrate its orbit forward and backward, you can show that even as recently as 75,000 years ago, a clone, and therefore I'm not saying that this is the real object, I'm just saying it's a possible evolution. This object could have fallen into a short period orbit with a perihelion distance inside the Earth's orbit for a period of about 5,000 years, as recently as less than 100,000 years ago. And then what would that object have seemed like? It's a massive object, 200 kilometers across. The amount of dust that it would have deposited in the inner solar system would have been huge. Maybe its fragments would have been huge as well in number, and maybe it would have had a major effect on the Earth. And that scenario is simply not accounted for in our present standard model of the near-Earth object hazard. And I emphasize, this is not likely to happen tomorrow or even the next day, but this is the sort of bigger picture in which the Earth is sitting as a planet exposed, if you like, to its near-space environment. And it's in that sense that history and perhaps archaeology may help to inform us of the types of phenomena that could have occurred over thousands of years, which we have no experience of in our scientific record, but which humanity as a whole might have had. And if I can develop this speculative story in the last few slides, I will just do so now and emphasize that it's reasonably speculative, but on the other hand, this is the question of making sure that we're not blinkered in our approach to these long-term risks and long-term natural catastrophes. So here's a picture which shows the effects of impacts graphically. Here's the canonical asteroid killing the dinosaurs, and you see it just punches through the atmosphere. The front end reaches the ground before the back end has finished going through the air, and it makes a crater 200 kilometers across. Here is the Sikhote-Alin meteorite, again, much smaller object, and this is a result of the Tunguska impact in Siberia. And when you go to Tunguska, it's in the middle of nowhere, it's 70 kilometers from the nearest trading station. What have the, if I can call them this, the down-to-earth Russian scientists gone and done? They've trekked 70 kilometers over the taiga through the mosquito-infested sort of environment, and then you sort of go down a dip and up a ridge, and they plant this totem pole. And they don't believe a word of it, but nevertheless they've done it, and they planted a totem pole to the Siberian god who brings fire to the forest, Akbi. And the mythology is that you must lay a trinket, a bus ticket, a coin, at Akbi's feet to ensure you will return. And what you have here is a 20th century illustration of how mythology gets there. It gets written into the culture of the community, even though the people doing it didn't believe it, but they've gone and done it. So that's a curious thing to me. And if we look at comets, this is really just to point out that their orbits, their physical characteristics, and their numbers all vary on timescales of human concern. They also can contribute to near-Earth objects, and they produce trails or meteoroid streams that intersect the Earth's orbit. And when the Earth goes through some of these trails, it's like a ball going through a bowling range, and you have an opportunity either to hit them or miss them. And sometimes you go through a really dense trail and you get a meteor storm, as it's called, like that. So what are the implications of this general picture? On the million-year timescale, you'd expect a few Earth-impacting kilometer-sized NEOs, near-Earth objects. You'd expect some giant comets. You'd expect some Halley-type giant comets in short-period orbits, and therefore recurring in their orbit until they break up. You'd expect a few thousand long-period giant comets also producing dust in the solar system, and maybe 10,000 Earth-impacting Tunguska-sized objects over the course of 1 million years. And some of the evidence for this I just mentioned, Encke's comet, the Kreutz family, the sun grazers in other words, and the dense Taurid meteor stream. And then at this point I possibly begin to lose some of you, but nevertheless the obsession, as I call it, of ancient society with celestial events. And what do I mean by this? Well, it's pretty obvious. Ancient scientists, societies also, were obsessed by the sky. And they took a keen interest. Here you see them. There's Stonehenge. And the Babylonian expert Neugebauer mentions that astrology can be much better compared in the ancient world with weather prediction from phenomena observed than with astrology as we now know it. And they almost suggest that there's knowledge, therefore, of a direct link between something up there affecting something down here on the ground. There's a lesson there for our modern way of looking at things. And consistent, therefore, with more activity in the sky in the past than there is now. Was the sky different in those days, maybe proto-historic times, than it is now? It's very puzzling if it were, because we don't really understand how it could be. But nevertheless, this is what the suggestion is. And here's another one, ancient Greek mysteries. The problem, if you like, of the Milky Way. Those of you who study cosmology will know that the ancient cosmologists came up with a really peculiar theory of the Earth and the cosmos, where the Earth is kind of a small disk, and it's surrounded by hoops of fire, a surreal picture of the stars and the celestial environment. Aristotle talks about the Milky Way being below the moon and the hot accumulation of the disintegrating products of comets. Where do you get that idea from? Anaximander, the stars lie below the sun and the moon. Metrodorus, the Milky Way is the former path of the sun. Now, what is that coming from? And does it lie in the shadow of the Earth? Of course it doesn't. The Milky Way is the plane of our galaxy, nothing to do with the Earth. And yet there is a phenomenon which is the product of disintegration of comets and asteroids, in fact, the zodiacal light. Here it's imaged, here and here. And if there were much more dust in the past, then that is a very natural way of describing the Milky Way. And if that dust then faded away, leaving behind, as it were, the normal Milky Way, you can understand the transference of ideas and how we're left only with the residue of the thought that the Milky Way is the former path of the sun. Now, I emphasize that no astronomer has yet explained how that could happen, but there you are with some evidence that maybe it did happen nevertheless. And so, just to wrap up now with 2 more slides, the extraterrestrial impact hazard is a unique risk. It also represents a unique conjunction of difficulties for conventional risk analysis. We don't have any recent claims experience, fortunately. The potentially unbounded consequences would be intolerable for us, or except that it's a very low chance event. And yet the thing has a global reach, so which one of us as nations has the responsibility to act? And then who controls them? The actuarial approach, the insurance approach, it seems to me, does provide a rational way to rank risks. And that, I think, can be applied to all risks, so long as you can agree the cost. It doesn't make sense to spend thousands of pounds investigating the loss of a biro from someone's office, for example. That would be an example of madness, but it does seem to happen sometimes. Here we have an example. So the impact hazard is high risk, a precisely predictable time of occurrence, because you know the orbits, and it's potentially avoidable and has all these other implications. So here we are. Astronomy turned out to be useful. As a result of curiosity-driven research, we live at this special time. Not just special for us, but special for the history of life on the planet. We recognize Earth's place in the universe. We recognize that the Earth is an open system, open to its near-space celestial environment. Not everybody accepts that paradigm shift. We're living through it, and so it's very hard to identify something which we're living through. But nevertheless, that is the case. And we also know that impacts hold the key to the long-term development of civilization and, in fact, the evolution of life on Earth. And for the first time, it seems, in the history of life on Earth, maybe in the universe, who knows, these facts are broadly known, and we have that knowledge. So it's an interesting question whether we'll rise to that challenge. I'd like just to finish with a quote. It's a slightly abstracted quote from Stephen Tolman in his book, The Return to Cosmology, in 1985. He's a historian of science, or was. Human beings are the beneficiaries of history. Our fate within this historical scheme depends on the adaptiveness of our behavior and on the use that we make of our intelligence in dealing with our place in nature. Thank you.
Well, what a lot of junk there is swirling around us in space. It's a chastening thought that one of those lumpy pebbles that we saw pictures of doesn't even have to be big as the Gog-Magog Hills, and they're pretty small, to erase the whole of the human species from the planet. I have found it a fascinating talk, partly bringing it at the end to the question of how previous societies have put up their Stonehenges or whatever as a way of doing something to come to terms with forces that are not only uncontrollable but catastrophic. And it raises, of course, this fascinating question of how long we should expect our species to survive, given that we're making a pretty good job of wrecking the planet on our own without external help. And perhaps we should have the humility to improve life as it is rather than to strive for eternity. Thank you for a very stimulating thought.
Thank you.